So now we're going to look at 8.2.1, which is a section on distinct real eigenvalues. So 8.2 is broken up into three pieces. So first, let's start with our theorem. So we're going to let these lambdas be n distinct real roots of the homogeneous system. We'll look at non-homogeneous in 8.3. And x prime equals ax. And we're going to let our k1, k2, all the way up to kn be the corresponding eigenvectors. Eigenvectors, sorry. So the lambdas are the eigenvalues. I guess I should put that up here. These are the eigenvalues. And then the k's are the corresponding eigenvectors. And so the general solution to this is x is c1 k1 e to the lambda 1 t plus c2 k2 e to the lambda 2 t all the way up to cn kn e to the lambda n t. So that's what our general solution is going to be. So the steps in solving the system is, one, we have to find the eigenvalues. And we're going to do that by taking the determinant of a minus lambda I, set that equal to 0, and then from there we'll get the characteristic equation. Once we have that characteristic equation, we factor it or whatever that we need to do so that we can find exactly what those eigenvalues are. So that's the first step. The second step is to find the associated eigenvectors. So we have to find the vectors k, the kn's, and we're going to find that because it's a minus lambda I, right? Because we'll already find the eigenvalues, times k is equal to 0. So we'll solve for those. And then lastly, we're going to write it in general form. So this is our general solution up here. So our first example, I want to solve dx dt is 1/2 x plus 9y, and dy dt is 1/2 x plus 2y. So the first thing I need to do is to write the associated matrices. So x prime, and then it's just the coefficients, so 1/2 and 9, and 1/2 and 2. So that's the associated matrix. So I want to find the lambdas. So I need to know what those eigenvalues are. So I need to do a minus lambda I. So my a was 1/2 9, 1/2 2. And the reason why it has to be lambda I is because I can't subtract a 2 by 2 matrix with just a vector that's 2 by 1, right? They have to be the same size. So we're always just going to take the lambda and multiply by the identity matrix. So that's what that I stands for. So I have lambda 0, 0, lambda. So this is lambda I. And I subtract it entry by entry. So I have 1/2 minus lambda 9. And then 1/2 2 minus lambda. So that's what I need to take the determinant of. And when we take the determinant, it's a 2 by 2, so it's nice. We can just do the cross products. So I get 1/2 minus lambda times 2 minus lambda. And then in the other direction, I have 1/2 times 9. So I have minus 9/2. So I'm going to multiply that out. I get 1 minus 1/2 lambda minus 2 lambda plus lambda squared minus 9/2. So just rewrite that and clean it up. We end up with lambda squared minus 5/2 lambda minus 7/2. And we need to set that equal to 0. So now I have my characteristic equation. So here's my characteristic equation. And I need to solve it for lambda. So I'm just going to rewrite that. Minus 5/2 lambda minus 7/2 equals 0. Now, I really don't want to factor with fractions, so I'm going to just multiply everything by 2 so I can clear them. So I get 2 lambda squared minus 5 lambda minus 7 is equal to 0. I can factor that. I get 2 lambda, I need a 7 there, and a 1. And I want my middle term to be negative, so it's going to be 2x minus 7 times lambda plus 1. So lambda 1 is 7 over 2, and lambda 2 is negative 1. So here, again, I'm in the real distinct eigenvalues, my first case. So now that I have that, I need to find k. So we know that a minus lambda I times k is equal to 0. So lambda 1 is 7/2. And I just need to take my original equation, which was 1/2 9, 1/2 2, and subtract lambda I. So what that's going to do is just put my eigenvalues on the diagonal, zeros everywhere else, no matter how big the matrix is. And when I subtract them, I get negative 3, 9, and then 1/2, 2 minus 7/2, negative 3/2. So this is a minus lambda I. And now I have to multiply that by k. So that vector k, we're just going to have different entries, k1, k2, and so forth. So I have negative 3, 9, 1/2, negative 3/2, and I need to solve for k1, k2, and that is equal to 0. So multiplying across and down, we get negative 3 k1 plus 9 k2 equals 0. And then the other row, we get 1/2 k1 minus 3/2 k2 is equal to 0. So if I solve this for k1, I would just move k2 over and divide by 3. So I get k1 is equal to 3 times k2. For this one, I'm going to do the same thing, solve it for K1. So if I move it over, I get 1/2 K1 equals 3/2 K2. Divide by 1/2, and we still get K1 is equal to 3K2. So these two are exactly the same. So I'm just going to pick K2 equal to 1. I like to deal with whole numbers if we can. And therefore, K1 is going to equal 3. So for my first eigenvalue, I have 3, 1. Alright, so my second one. My lambda 2 is equal to a -1. So I have to do the same thing. I'm going to start with 1/2 9, 1/2 2, minus, and then the eigenvalues again are on my diagonal. So I have 1/2 minus a -1, which gives me 3/2. 9 minus 0, and then 1/2, and then 2 minus a -1 gives me 3. So this is my a minus lambda I. And I have to multiply it by k. So the first row, I get 3/2 K1 plus 9 K2. And the second row, I get 1/2 K1 plus 3 K2. And they're both equal to 0. Again, I'm going to do the same thing. So if I solve for K1, move the 9 over, I get -9, and then divide it by 1.5. That would give me K1 is -6 K2. And the second one, again, move the 3 K2 over and divide it. I get K1 is equal to -6 K2. So I'm going to, again, just to pick nice numbers, I'm going to let K2 equal to 1, which means K1 is equal to a -6. So my general solution -6, 1 is x equals C1 3 1 e to my eigenvalue was 7/2 t plus C2, and then this k was -6 1 e to the -1 t.